With Loopsense, we present a low-scale minimally invasive knitted resistive sensor that can be easily integrated into a wide variety of flatbed knitted fabrics. Our sensors are highly sensitive and responsive and can be scaled down to an absolute minimum of a single knitted loop. We investigated possibilities in loop meshing to find configurations that enable us to discern between actuation modalities of horizontal and vertical strain as well as pressure. The sensing principle is based on the interface effect of a force-sensitive resistor, where external forces increase the surface contact areas, which leads to a change in electric resistance. Traditional solutions of knitted force sensors consist of a larger area, as well as multiple materials to implement conductive and piezoresistive parts. This comes with considerable limitations for textile and UI design, as well as for integration into more complex structures. We use a flexible and durable Litz wire with a copper core and piezoresistive coating to combine all required materials into one single component. A force-sensitive resistor can therefore be established by a single intersection of those wires. We create loops of coated wire that provide these intersections at the intermeshing points between loop head and feet. To do this, we use flatbed knitting, since it is highly adaptable and provides loop-level control during design and programming processes. Combined with the design latitude that our low-scale sensors provide, we are able to integrate force-sensing cells that are barely recognizable in the final fabrics. Especially in two-faced fabrics, the sensors can be made entirely invisible on the front face. We created a line of 3 knitted fabrics that demonstrate our concept using 4 sensors that are distributed in an arrangement of 2 by 2. The resulting fabric devices are highly sensitive and responsive to actuation and can be used to sense deformation and activity on the surface. Furthermore, we explored the effects that different stitch types can have on the sensor's performance, since the loop meshing has a huge impact on the yarn interaction in the knit. We expected this would result in different characteristics and responsiveness with respect to actuation modality, straining horizontally, straining vertically, or pressing. We fabricated single-faced as well as double-faced samples to explore possibilities of sensor integration and evaluated these samples using an automated testing setup to investigate their response regarding strain and pressure. Results showed that the samples feature largely varying characteristics, depending on loop composition. This can be used to infer actuation modality by sensor fusion when different sensor cells are combined. In a first sample, we combined knit and tuck sensor variations in order to discern between vertical and horizontal strain. In a second sample, we added a miss variant as a third sensor to also detect pressure on the surface. For demonstrating compatibility with common knits, we show a knitted glove for tracking finger movements. Recognizing direction of strain can be useful for operating a slingshot. Furthermore, keys of a knitted keyboard can provide a velocity feature as well as integrated pitch bend. In our paper, we present further details about sensor integration into 3 exemplary fabrics, results of preliminary washing tests, as well as crucial insights regarding successful handling of wires in a knitting process.